Thank you. Well, I thank the organizers for giving me another chance to attend CIDER. This is my fourth. I had the pleasure with Richard Al and Cynthia Lee to even be a director of a CIDER in Berkeley, and all of those have been great. And this one has been no exception. Very fun so far. My presentation is on folding constraints into our models of flow in the mantle. And to some extent, it would have been nice to have another convection geodynamics lecture in between, so I'm going to be coming back to some of the fundamental concepts and trying to sort of map them into the Earth. Now, the overall goal of such efforts really is to link the observations that we have on the surface of the Earth in the oceanic realm, back to maybe 200 million years or so, and in the continental realm, back to 3.5 billion years or so, to the internal structure and dynamics of the Earth, including what is happening in the core, and sort of encompassing the global flow dynamics is the objective of this summer school. And if we have an understanding of how convection works, that then allows us to really bring these different components of the Earth system together, right? And this is where, to some extent, things have to be going if we want to understand the overall behavior of the planet. Just some introductory comments here. What I'm showing you is one of those attempts where folks have linked reconstructions of the surface of the Earth, plate tectonic reconstructions, with a convection model, predicted deep mantle thermal structure and thermochemical structure. And that's nice. So you can sort of try to infer what the mantle looked like about 200 million years ago. And that structure at the core mantle boundary then talks to another part of the deep Earth system, the core. And so what Peter Olsen has done here, he's taken the heat flow that's indicated here, high heat flow in the circum-Pacific ring of subduction, imposed it on a geodynamo model, and predicted the magnetic field. And one of the interesting outcomes of this particular modeling exercise is that the dipole is strong at 200 million years, but it's tilted, right? And so this tilt from the spin axis of the Earth is an interesting, perhaps temporary violation of one of the fundamental assumptions of paleomag that went into this reconstruction, that the dipole was always aligned with the rotation axis, right? And so for those sorts of models to have any meaning, right, one of the assumptions is that we have a general understanding for how mantle dynamics and how plate tectonics works, right? And this is something that's true to first order. I'm going to proceed to show you some examples for why I think that is true, but it's something we have to question, and is of course not exactly true, right? And so the whole enterprise then focuses on evaluating how much of the physical foundations that went into the model are robust and what aspects of those are uncertain. Now, as Michael said in the first geodynamics lecture, the answer as to how does plate tectonics work is that, well, plate tectonics is simply the cold top surface boundary layer of a convecting mantle. I have a little movie here which improves slightly on the realism of a Rayleigh-Taylor perfectly symmetric convection cell by introducing depth-dependent viscosity. That's why these things have different behavior at this viscosity jump that's somewhere up here. And I've introduced temperature-dependent viscosity. Not that this is a realistic approximation of the Earth, but this is perhaps a little bit closer. And over these 2 weeks, we're going to explore several models that are increasing on the realism. So this is true, and then we can kind of go home. However, this system, just by looking at the convection system, it's a little bit hard to link what is going on to surface observables and to extract particular components of the system. That is why people like to often talk about plate driving forces. Right? The plate driving forces in a convection model are naturally incorporated by the balance of the forces and the conservation laws that Michael explained. But sometimes it's nice to take a subset of that convection model and draw one boundary and isolate, for example, the plates and talk about something like ridge push. Or we would like to isolate the slabs, slab pull, or we consider large-scale flow, or we consider the effect of gravitational potential energy variations, basically building mountains and mountains' tendency to flow apart. So once we have these subsets, once we define these integrals, then things get a little bit trickier, right? But it's still kind of helpful to understand components of the system. Taking the half-space cooling model that Michael introduced, that is one of the major achievements really of geodynamics in that it explains about 70% of the ocean's bathymetry. We can take this same half-space cooling model that describes the thermal boundary layer dynamics and integrate it in different ways. We can integrate from the ridge down through the thickening thermal boundary layer. The pressure here has to remain constant at some basis depth from isostasy, but as a function of depth, the pressure within the lithosphere can be unbalanced. That leads to lateral forces. We can integrate over these forces and have something that's like a lithospheric thickening force. That's also called ridge push. We can do this integral along the plate, or we can worry about what happens when that boundary layer goes down. As Magali explained, here's a thermal model of the lithosphere. If we just flip it around, we can integrate the buoyancy force of this subducting half-space layer, and we get an estimate of the slab pull. If we do that exercise, it turns out ridge push usually ends up to be about a factor of 10 smaller than slab pull. Of course, this is very approximate. And so this is telling us that based on our understanding of half-space cooling, there should be a dominance of these slab pull forces compared to the lithospheric thickening forces. Down here, just a reminder that half-space cooling is reflected to some extent in other observations from the deep Earth seismology, and Jean-Paul just discussed some of the complexities. So this is nice. There's a theoretical prediction, right? We're building on this half-space cooling model. Now, Forsyth and Yater, we're going out to the Earth. We are treating individual plates as realizations of the same experiment, and then let's check how does the plate velocity relate to trench length. And it turns out that indeed the fast-moving plates have a larger amount of slabs attached. So this observation, this scatter here, this correlation is consistent with the predictions from the half-space cooling model. Right? There's a simple example how we can take our theories, use the Earth as different realization of the experiment, and confirm them, sort of to first order. Many of the other correlations are quite poor, and this slab-pull correlation is a quite strong one. Now, with more mathematical effort and more physical modeling effort, we can set up a higher detail model of plate driving forces. And this is what I'll spend the rest of the talk on, basically explaining the different ingredients of how we do these global circulation models. Here's a result from Alex Forte's work, showing you in green observed plate motions, in blue the model predictions, and you can see that for this particular model, which has certain assumptions that we're going to come back to, the match is almost perfect. Right? So given certain assumptions on the physics and the internal structure of the Earth, we can perfectly explain plate motions, right? So in this sense, we do know how plate tectonics works. For this to be a valid physical model, it is important that the plates cannot have homogeneous rheology, but we have to have weak plate boundaries. Well, it's not a surprise. Plate tectonics says, in its most strict formulation, that all of the deformation is happening in infinitesimally thin plate boundaries, right? And so we cannot just have a strong layer. We have to break this layer, make it weak, and then we approach something like plate tectonics. We now have groups, not me personally, the community has access to numerical tools that can set up the problem in very high resolution and global scales, and we can ask, for example, what is the best power law exponent, coming back to Uli's talk, here N, and what is the best yield stress, for example, that gives me the right predictions for the plate velocities. Right? We can do these tests at pretty much arbitrarily high resolution. But that then takes the Earth as it is and prescribes the plate boundaries. Right? That does not answer the question, well, why do we have this particular style of plate tectonics? We've also made progress along those lines, following on years and decades of research and really a big push by Paul Tackley and his group in the early 2000s, we now understand that we can generate something like plate tectonics, where these are surface viscosities and those are velocities, if we have a temperature-dependent viscosity that makes a strong lithosphere, and if we have a yield stress that breaks it. And here's a computation that's run at a Rayleigh number that's too low, but it has some interesting properties. And you can see, for example, here that in this system, it's not the Earth, but it's an Earth-like planet, we get subduction, sometimes straight down, and sometimes rolling back, looking almost one-sided here. And so we have a feeling here there's bits and pieces missing, such as transform faults, but we're getting there. And we can look at other, and once we have a planetary scenario, right, then we cannot really compare with specifics of the Earth, but we can compare things in a stochastic sense. I'll be mostly talking about global experiments. For global experiments, it's always useful to come back to the spherical harmonics that Miyake introduced, that we've seen in several talks. Just a reminder, all these things are spherical equivalents of a Fourier decomposition. We have cosine and sine terms, and we have these degrees. The higher the degree L, the more of these cosines do I fit in the Earth, and here's different realizations of L and M's, and then we have these zonal and these sectoral contributions, right? And they look like the normal modes, and they look like your quantum mechanical mobility distributions. You know, and it's not a coincidence, but we can use these things to analyze the wavelength dependence of structure. And so, for example, we can hopefully move on here. Maybe not. I see, this is what happens when you put up equations. All right. Huh. All right. Sorry about that. I did test this about 3,000 times. Let's see. So what we can do, and Barbara showed this already, we can take observations of the inferred structure of the Earth from seismic tomography, and we can ask, well, what does the heterogeneity character look like moving away from identifying individual geographic features? And that's done here in a power spectrum plot, where this is the spherical harmonic degree from long to short wavelengths, and here's depth, and this is normalized for one particular model. And you can see that most of the power resides at these very long wavelengths, basically this sort of ring of fire circum-Pacific zone of subduction, or these red blobs that are sitting in the lower mantle. And these models of the general plate tectonic generating kind do provide a prediction of a power spectral structure that is not too dissimilar for what tomography sees. And that's not a coincidence, because plates themselves impose structure on convection that is very different from the structure you would get from simple Rayleigh-Taylor convection. So if you have plate tectonics, you should better organize deep structure in a way that's consistent with it. But you can use the depth distribution of this coherence, for example, as another indicator. So we sort of know aspects of plate tectonics. Yes?
In the plot on the right, the mantle simulation, what's the explanation for the increase in power at about 1,700 kilometers depth?
This is basically where slabs peter out, and it's very much dependent on the degree of internal to bottom heating. Something I'm going to briefly come back to later.
That's not seen in the system.
No.
So that's just a modeling constraint? Or that's as a result of the the model model parameters you're using.
Yes. And this was never sort of meant to mimic this. So we did not ever tune this to match that. I can show you slides from different computations by a different group that look even more like tomography. But my point here is that things are not too dissimilar when we do these things. And the main point is there are aspects where it's useful to look at heterogeneity character, because we're not expecting, unless we're certain researchers, to have Tonga pop out of a generic model. Right? We're just looking at the heterogeneity character. All right, so the flip side of this is, well, we don't know how plate tectonics works, right? And there was one example how the model did not match the observations, right? And so there are some first order things where we're really sort of just beginning to understand what's happening. Here's, for example, something I like, the area per age, the distribution of seafloor age as a function of age. And that is well known to have this very steep decay, an almost triangular distribution. And if a thermal boundary layer, right, where everything that we're controlling the subduction of oceanic lithosphere, we would expect that there's a critical age when slab pull is just so large that everything gets subducted, and this distribution should look something like that, like a box. Turns out when you go back in time and you believe these reconstruction, there is a fluctuation in this distribution, and it's apparently explained by sphericity of the Earth, interactions of the oceanic system and continents, but something we're just beginning to understand. So there's a first order constraint where at least the present day age distribution looks quite a bit different. Now, Magali already illustrated some of the complexities of subduction and the issue that we still don't really know the rheology of slabs, and we don't really understand the effect of phase transitions after decades of research, to the extent that if we are pushing things around at the surface, slabs do not look like what we think they should look like based on tomography and seismicity. So many groups have taken a hybrid approach where they're prescribing plate motions, and then they're even prescribing the trajectories of slabs into the mantle, and then are asking different dynamic questions. So there's a real problem here in that it's hard to bring everything together still in a dynamically consistent way for specific questions. Right? It always depends on the questions you're asking. And those models are really nice for certain questions, but you cannot use them to say anything here because that's, of course, prescribed. And as Michael mentioned, the reason for this is that the effects of rheology and the effects of composition are making things being thermochemical convection in the mantle more interesting than in a Rayleigh-Taylor scenario. I like to show these plots because looking at the surface of the Earth, we can compare the Pacific domain, that is the closest to a simple plate tectonic model to a simple oceanic system, where the African domain, where we have a huge continent sitting there, which is the product of fractionation, which has very different dynamics. And the counterpart of the strong compositional anomaly is perhaps in the deep mantle, these two piles that we have, where we really have to worry about composition. We may have to worry about composition everywhere in between, but for sure the continents, particularly the old continents, and these piles are different compositionally. Perhaps everything in between is okay in terms of being purely related to temperature. And then we have to worry about the rheology, what is making these plates, and that's a convection model that has continents gone crazy because the buoyancy number is wrong. So here's the dilemma. We have a pretty good handle on some of the physics. How can we use constraints from the present day Earth and from the past to further refine these models and build a better working hypothesis if we want to do planetary evolution? I'd like to walk you through some of the constraints we have, not all, some of the major ones first, and then I'm going to hopefully address how the community has gone about incorporating these constraints into models. Let's start out with plate velocities. Here's the Morvell 56 plate model by Argus and Demetz and others in a reference frame I like. The vectors showing you which way the plates are going. The background coloring, this shouldn't have a little triangle here, is the absolute plate velocity. I like to show this kind of plot in my intro classes because if you color it like this, you immediately see where the Euler poles are, right? And how the motion of a plate on the surface of the Earth is this rotation around the Euler pole, right? Pacific plate Euler pole goes like this. Indian plate Euler pole goes like that. And this particular reference frame, Antarctica is not moving at all. And so you can see the ranges of the velocities. You can also see immediately that the oceanic plates, the plates that have mainly oceanic material on it, moving faster than the continents. Right? This is to some extent going back to Forsyth and Ueda because those are the ones that have the slabs attached, right? But there's perhaps a little bit more to that. Plate velocities include information about the relative motion of the plates, but also, in a general sense, if you allow for non-plate-like behavior, you have variations in the distributions of strain rates, right? In reality, if we look at GPS, for example, things are not localized in infinitesimally thin zones, but in some places, such as in the western United States, you have a broad region of deformation. So there's some information, or in Asia. So the distribution of strain rates are in here. Relative plate velocities are information. The absolute plate velocities in some reference frame can provide information because the degree of spin, the net rotation, is something that geodynamic models are able to address. Moreover, we can take these velocities and Helmholtz decompose them into poloidal and toroidal fields, very much akin to the normal mode approach, or the decomposition of the wave equation solution into P and S waves. Poloidal velocities, if viewed from the surface, are the ones that have sources and sinks. Toroidal velocities are the ones that have spin only. They're irrotational. You can write it down like this. There's two potentials. This one does you take the curl. There's no spinning. This is 0. Here there are no sources. If you look inside view, the poloidal flow, that's associated with moving hot stuff up and cold stuff down. From an energetic point of view, a homogeneous fluid has no reason to do this toroidal thing because it's just moving away things sideways and shearing things, inducing viscous dissipation that doesn't help with the convection system, right? And so understanding how this partitions for the Earth helps with this rheology problem. We can do this in Cartesian, or we can do it in spherical harmonic space, and the vector spherical harmonics were introduced yesterday already. I'm using the same thing here. If you use it, you're looking at azimuthal anisotropy that has 180-degree periodicity, you have to use generalized spherical harmonics. So we can take the velocities from a plate reconstruction here. Here, Müller's recent, the Earthbite group's recent reconstruction. We can then just do some statistics on it. Take the component that's poloidal, take the component that's toroidal, and plot its ratio, which is this purple line here. And it turns out that for the present day, there's about 60% toroidal power in the part of the field that is higher degree than degree 1. The degree 1 toroidal motion, that's the net rotation. That's the spinning of the Earth in some reference frame. And that is shown here in green. I might come back to that later. But that's interesting. And so if taking this at face value, there was an episode where there was a lot of sort of stirring about 50 million years ago. And then this ratio of stirring has been fairly low back here. And that would say that at 150 MA, the system was very efficient in getting the heat out compared to the strike slip motion, right? And then we can worry about what this means, if this is real, and the uncertainties of these reconstructions, which to some extent also rely on geodynamic assumptions. And of course, the further back in time we go, the larger the uncertainty in any of those kinematic parameters. So there's lots of information also on the time evolution of convection in those plate reconstructions themselves. Another first order constraint that is actually much harder to get to is the actual topography of our planet. Again, we look at this, right, and we see there's continents and oceans. So something has fractionated. This is not just a planet that's thermally convecting. This is a thermochemically convecting planet. We know the half-space cooling explains much of the oceanic seafloor, but what about the topography within the continents? What about this record, right, of geological deformation? The major contributing factor is not one that's related to convection at the present day, but it's one that's related to previous deformation episodes and that is now statically recorded in the lithosphere, and that is the effect of isostasy. Right? If you have a thicker crust, floating equilibrium tells you that a mountain should form, or vice versa. If you see a mountain and it's in floating equilibrium, you will have a thicker root like an iceberg. So you can work out the contribution of the crust, and it depends on the density of the crust in the asthenosphere. And changes in the crustal thickness will lead to quite large variations in topography. Changes in lithospheric thickness will lead to relatively small variations in topography. And the typical classification into Airy and Pratt isostasy implies that, strictly speaking, density is constant, and we have variations in thickness, and that sort of works for the continents in terms of the crust. And Pratt says, well, the thickness is constant and the density varies, and that sort of works in the ocean as we explore a little bit further. Simple concept. And so if we want to understand how much of this is static and how much of this is not isostatic, so somehow related to convection, we need a crustal thickness model. Here's a very good one, but it still has lots of gaps in terms of the coverage, particularly in Africa, for example. And you can see in just eyeballing it, yeah, this sort of works, right? High topography in Tibet, high crustal thickness. We can plot the correlation here. We can plot crustal thickness that is corrected to some extent for density against elevation. And overall, this is kind of nice. And here this dotted line is assuming a constant lithospheric thickness of 100 kilometers. Right? So overall, yes, isostasy is still okay 200, 300 years later, but we have this big residual. Right? And sometimes there's kilometers of being out of whack in terms of topography. So that's interesting. We can take this crustal model, play our games, and then come up with a residual topography estimate. Right? That's a model, right? It's not a real datum, but something we might want to explore.
Thorsten, on the previous plot, what's all the negative topography?
Oh, those are oceans, right?
So I was told once upon a time that the oceanic crust was 7 kilometers thick.
Yeah. So these are there's scattering in there, and so this is trying to account for hotspots and places where you have thickened crust. But I would not put much weight on that, right? But those are taken at face value. Fluctuations around 7 kilometers in that crustal model. If you're really worried about the crustal thickness, you very, very much have to use active source constraints, right? You have to go to the places where this is well measured and is not here. This is just for the sake of argument.
But I interrupted to ask this question because if you get rid of the oceanic crust, there's a terrible relationship between topography and crustal thickness.
Geochemistry. You make up your mind if this is terrible or not. Right? I think it is terrible, and I think it's worthwhile exploring, and I think there are significant deviations, and I think this is interesting. I used to hate it, but I think the crustal models are getting to the level where this is a useful thing to explore. And I'm totally happy if you want to take the point of view that isostasy is not a very good model in many places. I'm happy with that statement. The problem, though, being that lithospheric density variations are not folded in here. And you can almost always build a model that has very strong lithospheric density variations to get rid of any mantle effect. That's where the issue comes in, right? But airy isostasy is kind of bad, and I'm going to come back to that. Well, here's one thing that we can take as something to match. Now, talking about things at the surface, we can also look at the overall gravitational shape of the Earth and look at the geoid. The geoid is the equipotential surface where once we take the derivative, we get out a constant gravitational acceleration. It corresponds to the sea level, to the wave height if you average out the waves over the oceans. In this crazy image that's in all the textbooks, if you build a channel throughout all the continents, it will be the water level in this channel. Now, because the Earth is spinning, the major signal is an ellipsoidal deformation, right, from the sphere, as you've learned in your intro geophysics class. Now, that ellipsoidal deformation is not quite the ellipsoidal deformation you would get from a spinning hydrostatic Earth. So if you look at a geoid anomaly, as I've done here, and I hope I can advance the slide after this fancy movie, then you have to be careful how, you have to ask, how is it corrected? Did someone take out the major ellipticity or the hydrostatic shape, as I've done here with some model? And even these models, there has recently been some change. But that being said, you can see there's these bumps over the subduction zones, part of Western Africa, and then there's this interesting low, for example, in India. And that's sort of, nice. And we can ask, well, what is the spectral character of this deviation? And then, given the nature that this is set up, we can also prefer to look at gravity. Now, the geoid, U, that's the potential, and the gravity, G, is the gradient of this potential. So they are the same thing, but if I compute free air gravity here in green, because of pulling out the wave number from that spherical harmonic expansion, I get a much rougher spectrum, where this is degree and this is power. So the geoid looks redder and the gravity looks whiter. And some people like to look at gravity because, as we'll see later, there's a different depth sensitivity, and you weigh the long versus the short wavelengths differently, but it's the same thing. Some people also love to compute gradients of gravity, which is very helpful to bring out details, but keep in mind what the satellites are measuring is one thing, which is the geoid. Okay, and so these are also called potential field constraints, geopotential field constraints, really same thing. So how do they link up with internal structure? Here's a nice sketch from Yannick Ricard. So the idea is, well, if we have an anomalous topography, part of that might be due to dynamic deflections of the surface of the Earth, for example, due to hot stuff rising, or vice versa, cold stuff sinking. And then on top of that is the geoid, and we're going to explore how the geoid feels these anomalies, because it's highly non-trivial, and it's perhaps, besides the Stokes velocity, the only thing I really want you to take away from this presentation, right? So the idea is, let's build some sort of model and see if it matches. How do we build the model, right? If we want to ask, well, is this bump underneath India due to some internal load? We need to construct a load model. So somehow make up these red and blue things. One way to do that, that's actually quite useful and quite powerful, because slab pull is so important, is to consider Wadati-Benioff zone seismicity at the places where the plates are subducting, and use that to construct an upper mantle density model. Right? Not a lot of assumptions, but you can basically assign a thermal boundary layer or something like that, look where the earthquakes are, and build a model. And Brad Hager did that, and you can make interesting predictions just based on that. You can take it one step forward. Still not a lot of modeling. You can look at plate tectonic reconstructions, such as the one from Müller et al., just as an example here. See where stuff's subducting, such as underneath Eurasia here, and then say, hey, it's subducting. Let me just drop some slablet, some ball, some Stokes sinker of cold stuff into the mantle, and then let it sink. Move to the next time step, drop in another one, drop in another one. By that approach alone, you get tilted slabs if the trench is moving in some reference frame. And then you can worry about, well, maybe, as Magali discussed, once the slablet makes it into the lower mantle, maybe I should change its sinking velocity, because perhaps there's stronger material down there. So you can construct a forward model of the Earth by dropping in slabs. What do you compare it to? Well, now you have to take it one step higher in terms of the analysis of seismological data, but we can look at seismic tomography. Here's some random model where the more since the late 90s, there's been an emergence of a picture that at some mid-lower mantle depth, there's this zone of blue stuff around the Pacific. And so we can ask, well, if we build a structure model based on slabs, does it match tomography? And for what assumptions does it match tomography? That's exactly what Yannick Ricard did in the early 90s, and then it was followed up on very nicely by Carolina Lithgow-Bertoloni and others. And what you find from the match of your forward slab model and tomography, very old tomography models here, the answer is exactly the same, that this works best if there's a decrease in the sinking velocity, maybe a factor 4 or so, between the lower and the upper mantle, right? All of a sudden now we've used our understanding about boundary layers subducting to say something about the interior of the Earth. In particular, there's a slower sinking velocity, presumably because of a higher viscosity. The cool thing about those subduction models is that they do not just record what's happening and give you a present-day estimate. To some extent, they give you estimates of the mantle in the Earth's past, illustrated here by where the trenches are in one of Bernhard Steinberger's models, or illustrated here, depth for present day in 56 MA from Carolina Lithgow-Bertoloni's models. And so that's nice because you can now say, well, let me use this density distribution and set up a different test for plate driving forces, right? I can say, do my assumptions that match plate velocities now also work back in the past. That's kind of fun. What you can also do, and that's something that was proposed by Vandermeer and others, you can go and look at small-scale anomalies in seismic tomography, here in Spachmann's P-wave model, and try to identify these little specks at the core mantle boundary with certain tectonic events. In this paper, the authors make the argument that they are able to do that back to about 200 million years or so. And so here's an example what they think plate tectonic reconstructions yield in terms of trenches at 250 MA. This is from Trond Torsvig's group, and they are associating these blue anomalies with those slabs. And that implicitly or explicitly requires a fairly slow sinking rate throughout the mantle so that you can associate things at the core mantle boundary with something that happened 200 million years ago. I think that sinking rate is a little bit too slow, but it's a matter of debate. And the neat thing is that this gives you longitude, whereas PaleoMac only gives you latitude. That's why it's a very intriguing approach.
The sinking rate is what, factor of 8 slower in this one?
Yeah, something like that. Yeah, and people have explored sinking rates by doing experiments such as this one. What this is now doing is it's taking Yannick Ricard's approach one step further, using by now perhaps outdated model by Bernhard Steinberger that not just drops these slablets, but also allows for the lateral advection of these slablets. And that compares the predicted structure with a particular seismic tomography model. And you can see, as a function of wavelength here and depth, that there's a pretty good correlation, but the correlation is limited to the longest wavelengths. And that is a real issue, even for more modern approaches, for creating subduction-based mantle models. The correlation with seismic tomography is never really higher, even at the longest wavelengths, which is shown here, than around 0.4 or something like that. And that is for the reasons that Magali discussed, that we still have a hard time getting the penetration, ponding, and transition of slabs through the transition zone right, which is a real bummer because mass flux through 660 is an important constraint for overall chemical evolution of the mantle. There's about 250 papers on that very same question, but I would maintain that the failure of our forward models implies that we're still not doing the best job we can in terms of how slabs make it through the transition zone. There's an issue here because it's not just slab rheology that determines this, but also the plate reconstructions. And clearly we have to follow with an iterative process and improve the plate reconstructions while we're improving our slab models, and the community is doing that. What is amusing to note is that if you compare these numbers for a slab model that basically says there is whole mantle convections and slabs are in the lower mantle, with a model that has moving plumes, the one that Matt mentioned yesterday. And now I'm comparing the slow anomalies from this moving plume model by Bernhard. Then the correlation with this particular model is actually better than for slabs. And I would maintain that this is true even for the newest models. So based on correlation analysis, we can make a stronger argument that tomography sees plumes than that tomography sees slabs, which is, of course, total heresy, right? Because most people would agree that, yeah, slabs make it to the lower mantle, but not all people agree on tomography imaging slabs. Here, incidentally, is Barbara's new model, the French et al., and it has roughly similar performance, but there's a reduction around the transition zone, which is interesting and perhaps worthwhile to be further explored. Now,
Thorsten?
yes?
Just, I guess for the sake of the students, to clarify that, you probably mean throughout the whole mantle, because in the upper mantle, there's no doubt that we're imaging the slabs.
Yes, absolutely. Thanks for the clarification. Now, with all of these comparisons between tomography and any sort of Earth model, it's useful to get a feeling for how well structure is resolved. And what we did here is we took published data, which the seismologists thankfully are very good about sharing, and we did our own inversions on a synthetic mantle model that had plumes and it had slabs. And the degree to which you expect this to be true will to a large extent be governed by what you think the ratio of internal heating to core mantle boundary flux is. Because as will be further explored in the next geodynamics lecture, I hope, here's our reference picture of Rayleigh-Taylor bottom heated convection, and here's what this thing looks like for pure internal heating. Right? That's the other end member, and the plumes have gone bye-bye. Right? So if you're purely internally heated, you don't expect any plumes. Turned around, if there's enough bottom heating, you expect plumes. Right? So this is just a fluid dynamical consequence of the thermal boundary layer. Anyway, so here's our model, and here's what a ray theoretical approach using modern data roughly gives you for this model. You know, individual models can do better, but this just gives you a broad idea. So here's the smoothing, right? If we think about this issue, is this a pile or is this a plume cluster for this particular data set, it would be hard to tell. In terms of the spherical harmonics that I showed you earlier, we are recovering everything up to about degree 15 or so. Right? And so that's a number to keep in the back of your mind, even without doing anything fancy. The things, the characteristics we're discussing that are below degree 15 are really resolved by global tomography now. What is kind of also interesting is if you then look at the intertomography model correlation over time, you don't necessarily see much of a convergence here up to somewhere, I don't know, maybe 10 years ago, but there seems to be an increase over the last couple of years. My point here, this is mainly a joke, right? And I will not explain what Ludwig Auer, one of the students I was working with a while ago, did to derive this model. But it's not just the data that goes in these models, but it's of course also the theoretical assumptions, right? And there's very different kinds of tomography. And here, by the way, is radial anisotropy, and it's much less well resolved, as we heard earlier, between these models. All right, so now we have seismic tomography. It's pretty well resolved. How do we convert seismic tomography itself into density structure? We can go to the mineral physicists, and we have a number of great lectures that are explaining some of the complexities. Here's one from Stixford and Johnlos showing you the derivative of Vs with respect to temperature and of Vs with respect to composition as a function of depth. So we can take these derivatives, we can come up with some sort of composition and do the scaling, and then have temperature and composition. Or we can turn it around, as Alex Forte and Steve Grant and Nathan Simmons have done, and either invert for best-fitting 1D scaling or invert for best-fitting 3D model of compositional structure or composition itself. So two different ways of approaching things. And here, inherently, you assume you know the physics because something's got to give, right? You have to have some hold something fixed to invert for something else. What I like to do is I like to take out the continents and multiply everything with 0.2. And that works quite nicely. And this is what happens when you take the tomography and you have, a couple of hundreds of degrees of variations. And that's, of course, first guess. But you can, pick your poison. All right, so we have the poison, we have the density distribution from seismic tomography. Now, how do we actually compute these global flow models, results of which I showed you earlier? How do we get these velocities out? All right, so we go back to the equation that Michael nicely introduced. I'm showing them again because I'd like to highlight a few things. One, that if we only have temperature anomalies, if we know the density structure, And if that viscosity here that sits in the constitutive equation is only dependent on depth, then we can solve this for a spherical Earth in less than a second. That's what you guys are doing in the tutorial. So that's very nice, and we can do this by breaking things down into these spherical harmonics. And that's kind of nice, and that's the circulation scenario. Right? There's no time dependence here. If we know the boundary conditions, and if we know the internal density structure, we know the velocities. End of story, right? There's no inertia, no weighting, no nothing. High Prandtl number approximation. Becomes more interesting if we, it all comes down, though, to the Stokes sphere solution that Magali already introduced, which is kind of fun. It tells you that the sinking velocity of a sphere scales with the density anomaly divided by the viscosity. This prefactor here depends on the ratio of the viscosity of the sphere to the mantle. Amazingly, it basically doesn't matter if you have a bubble or a cannonball. It also doesn't really matter if you have a sphere or a needle that's like this or like that. This thing sinks twice as slowly as this thing, which is not what you would intuit from the fluid dynamics that's all around us, right? Which is turbulent, but this is laminar flow, so it works differently. Incidentally, I don't have time to do this. If you define the Peckley number, diffusive to convective timescales, take a diffusive timescale that Michael introduced, plug that in, and associate this density anomaly with a temperature anomaly, then you get the Rayleigh number out of this thing. So it all hangs together really nicely with a slight complication that the length scale is not the length scale of the box, but the sphere. So that's cool. Keep in mind, when we're solving these problems, this is all we're doing, right? All of geodynamics is this equation. Almost. If we allow for compositional anomalies, we can define another compositional Rayleigh number here. And in reality, of course, viscosity is stress, temperature, grain size, volatile content, strain, and what have you content, and that's the strain rate here. Sorry about that. Okay, and that's when it gets interesting. That's when we have to use finite element methods. But we can do this now at arbitrary resolution, right? Unlike 10 years ago. If you give me a toe, I can compute the flow. It's really about the unknown rheology and the unknown composition. We can solve down to basically 1 kilometer resolution without any further assumptions, right? Which is quite useful. So we are more limited in terms of integrating the constraints rather than the numerical approaches to some extent. Of course, if we want to make useful science, we have to explore parameter space, so we cannot just do one huge computation, so there's other limitations here. Now, this is all circulation. Convection comes in if we include the energy equation. I'm not going to be talking much about convection, but that makes it nonlinear. This term here couples the temperature with the velocities, and that also, this energy equation messes up the reversibility. Advection, which is covered by the first two, can be time reversed. I can push things back, but diffusion cannot. So if we, yes?
What's in the delta symbol?
Oh, just this is the Kronecker delta because it's only pulling downward. The radial direction. Yeah, this is just a buoyancy force through the temperature, buoyancy force through the composition. All right, so we won't spend much time on this, but keep that in mind. So we can compute circulation. Let's start out, as Hager and O'Connell did in the late 70s, by pushing the plates and exploring the flow that is induced by the plate motion. What is showing here is old figure, the surface velocities in these solid vectors, and then the tractions that indicate the direction of shear underneath the plate. It turns out for the most part they align, but even based on plate-induced circulation, they don't always align, which is something that's good to keep in mind if you want to look at seismic anisotropy. Just for example, if you introduce density-driven flow, it's even worse in some places. Now, what about the geoid? Let's fit the geoid. So this is from Magali's talk a long time ago. What's the effect of a cold sinker? There's a static effect. If I sit on top of this cold sinker, right, if I do a gravity survey, I have to move further out to have the same pull because this thing is denser. So the static geoid anomaly is positive. However, because of Stokes flow, there's flow induced, and the topography will be pulled down. such that the overall effect for a simple model is actually negative. Slab sinker is expected to have a negative geoid signature. We can express this instead of using a single sphere, we can express it in spherical harmonics and can compute response functions of certain quantities, such as the geoid, the surface topography, and the CMB topography, to internal density anomalies of certain wavelength, long wavelength, short wavelength, and at a certain depth. So this plot shows you for an Earth model that has a homogeneous viscosity, if I put a wavelength perturbance of, say, degree 2 at the mid-mantle, the response of the geoid is negative. It's negative because it pulls the surface down and it depresses the CMB topography, and those are major density boundaries, right? And the distance to these density boundaries determines the gravity anomaly. This is almost symmetrical, this response here. Now, the kicker is, and this was pointed out by Brad Hager, Yannick Ricard, and Mark Richards in the mid-'80s, that this system responds entirely differently if you have a viscosity increase in the lower mantle. Here are the same response functions now. Let's look at the surface topography. Because this sinker couples less strongly to the surface, particularly if the density anomaly sits below that viscosity increase, I have a much reduced response on the surface topography for density anomalies that are sitting below that viscosity increase. The CMB topography is still depressed, but overall this means that the geoid is slightly positive, and I have a positive geoid response for long wavelengths, mid-mantle anomalies. Now let's look at the tomography, scale it to temperature, and here's what you get from the tomography, global tomography, and we can use the tutorial to explore these things in terms of a geoid prediction. Homogeneous Earth, here's our observed geoid anomaly, totally wrong, right? Negative over the subduction zones. Here's a model that has a viscosity increase, that has 4 layers, doesn't matter, and all of a sudden the response is positive. Okay.
What would be the viscosity contrast?
How much would it be?
Yeah.
In this model it's about 50, but we're going to explore this in the tutorial, and I'm going to talk about this a little bit in a sec.
If you go back one slide, the topography though depends on the elastic thickness, right? That you assume of the lithosphere, or how does that?
This is long-term fluid response topography.
Okay.
So it's not going to be modified by that, actually. Okay. So, but talking about topography, let's throw the topography back in. Let's go back to our airy residual surface topography I showed you earlier, and those of you with a keen eye will have spotted a clear half-space cooling signature. Right? It's not just airy, it's Pratt. And so the major signal here, by taking out the crust, is due to half-space cooling. And so there's a debate in the community, should I even call this residual topography? As long as we're clear on the assumptions, it doesn't matter. We can take it out, we can correct for the half-space cooling, and we can come up with a map like that. And that is now anomalous topography, taking out the half-space cooling, not considering that dynamic, and that would be the signal that has to be explained by mantle convection. This is from Bernhard Steinberger's work. And you see some stuff that's common in many models, big high over parts of Africa, western United States, and other features that I won't have time to discuss. And we can now say, well, how does this Stokes sphere talk to the surface? That's another interesting problem, and one that's illustrated here by numerical computation with a free surface for the aficionados. But what you get is that, well, the Stokes velocity scales with density by viscosity. Now, if you have a free slip surface condition, then the stress that's pushing up the surface should scale with the topography height. Stress is viscosity times strain rate. Strain rate is velocity over length scale. So I can plug this in, and the viscosity cancels out, right? Because a certain density anomaly drives a certain deformation. If the viscosity is high, your strain rates are lower, but you multiply with a larger number, so the stresses are higher again, right? It's a zero-sum game. So the topography scales with the density anomaly only to first order, and not the viscosity so much. Lateral viscosity variations will modify the wavelengths of expression, but not set the scale. What's interesting is if we're looking at time change in topography, such as the geologist might measure, that time change of topography goes with topography times the velocity, which turns out to scale as density squared divided by viscosity. So if you can measure topography and time change thereof, which is really hard, you can solve for density and viscosity. Or if you match the plate velocities and the topography, you can get at both the density and the viscosity. So this is neat. And yet to be explored really to a larger extent in terms of the time change of topography. But let's do it. Here are results from Bernhard Steinberger showing you that if you treat half-space cooling, which is imaged by tomography, as dynamic, you can get a very good correlation, 0.8 here between model, dynamic prediction from the flow computation, and the residual. And if you take out half-space cooling, the correlation is less good. It's about 0.6. But you can still explain some of these features. We can explore that, discuss that a little bit later. Now, this is a school on deep flow, right? We don't just have to look at surface topography. We can also look at CMB topography. This was done by a number of people, including a very nice study by Teresa Lassak and Al McNamara, which is shown here. Here's now a computation, not too different from what Michael showed, showing you the dynamic depression of the CMB for a purely thermal model. You can see the downwellings here push stuff down and vice versa. Pardon me? Oh, this is meters, so this would be 10 kilometers. Well, now, here is what happens if we add dense piles. This is still temperature. Here we have composition, thermochemical piles, and here's the effective buoyancy, which is the thing we want to look at if we want to do our isostatic computation. You can see that overall, these thermochemical piles are depressing the CMB, as you might expect, and Steve Grant was asking me about this. Thanks for bringing this up. But now it gets interesting, because the piles will have internal dynamics. And if we change the sorry, this should be delta rho. I apologize. This is an isoviscous computation. If we change it to one that has a factor of 1,000 temperature contrast between hot and cold, the internal dynamics of these piles work out such that you have different distributions of the effective buoyancy that are shifted more toward the center of the mantle, and you reduce the CMB topography. You can construct models where the piles actually have a very slight signature in the CMB topography. Now, CMB topography estimates from seismology at least used to be quite uncertain. Maybe this is something that's worthwhile revisiting, but with a note that the interpretation will depend to some extent on the dynamics, because the effective buoyancy is a little bit more complicated in this case. We can use the geoid now and the dynamic topography to do a little bit better in terms of inverting for viscosity structure. That has been a community effort since the early 90s. Here's an example by Panasuk and Hager, where they did a Monte Carlo approach and tried to fit dynamic topography and the geoid, and they found that there are these three families of viscosity structures that work equally well. We don't have to discuss those in detail, but there's a large degree of non-uniqueness in these geoid inversions, regrettably. Oh, this is probably 10 to the 21. And the geoid inversions are not sensitive to the absolute viscosity value. They're just sensitive to the variations of viscosity with depth.
This is the exponent.
Yeah, this is a log scale. What is sensitive to absolute viscosity variations is post-glacial rebound. Right? The viscoelastic relaxation of places that were loaded with ice, called glacial isostatic adjustment, because you have to account for the sea level equation, that was folded in by folks like Jerry Mitrovica and Alex Forte, showing you the joint GIA inversion up here. This is radius. Here's viscosity. Here's the GIA only inversion, and here's the joint inversion. If you do that, people will often throw the Haskell constraint at you. The Haskell constraint says that the average of the top 1,000 kilometers of the mantle under the places that are experiencing unloading, which are in cratonic regions that might be not normal, have an average viscosity of 10 to the 21. Here's what you get when you do a joint inversion. What is interesting, what Alex Forte pointed out to me in a CIDER-sponsored workshop not that long ago, is that the ice models that go into the GIA computations are still computed with different viscosity structures than the ones that are inherent here. So there's an opportunity to further close the loop, which is intriguing. All right, let's go back and let's briefly touch on some of the implications of these viscosity structures. Magali already showed that subduction zones show a remarkable diversity of behavior. Here, 4 different models, 3 different subduction zones, Tonga, Japan, Indonesia, showing you that sometimes slabs appear to pond at 660, sometimes slabs appear to pond a little bit deeper. And now there's sort of this interplay between observations from seismology, observations from mineral physics in terms of the phase changes, and these geoid inversions. For instance, here's an example from King and Masters in 92, where they actually have a jump in viscosity at 660 and another one at 1,000 kilometers, right? So there's some indication that there's some gradation in the viscosity structure with depth, and you'll have a chance to explore this yourself in the tutorial later today. So somehow the stalling has something to do with the viscosity increase. We can also go back to the seismological models and look at the heterogeneity again. For example, we can look at sort of same model correlation of one depth layer with the next and go through the depth of the model and compute the radial correlation. Here, radial correlation functions for 4 different models by Simmons et al. In blue here. In red, this is the one that Steve Grant was involved in. Strong decorrelation between 600 and 1,000 kilometers, and another drop in correlation at 1,900 kilometers. Here's French and Romanovitz, here's Savani, and so there's some interesting sort of inherent drop in this zone, but it's not really clear where exactly it is, but it appears to be in this range, right? And so this is from the models. The models have assumptions on parameterization, on radial damping, and what Lapoboski and I did is we asked the data themselves, which is an interesting exercise you can do. Early Harvard models had a discontinuous parameterization at 660 kilometers, which I also thought was interesting, but also somewhat limiting. And so what Lapo and I did, we took different data sets, body wave data, surface wave data using fundamental modes and overtones, P-wave data, and we asked how much is the fit to the data improved if you allow for decorrelation at a certain depth, and then we cranked through the depth regions where we allowed for this decorrelation. And what you see here is that, again, this range underneath 660 seems to be preferred, and there's a subtle indication that the best performance is somewhere around 800 kilometers or so if you allow for this decorrelation. And Max Rudolph will discuss this in much more detail, I think, next week.
So just a point is that this decorrelation becomes much stronger at long wavelengths. And I think that may be significant. I think it's probably...
Yeah, and so I think Max Rudolph is going to
explain.
explore this at much depth. That's why I don't want to talk too much about it. So, but let's sort of begin to wrap it up and go back to this fundamental observation of the plate velocities. And so if we take this model, right, the ones we just used to fit the geodynamic topography, and we compute the mantle flow at the surface, at a free slip surface boundary condition, this is what it looks like. And here are the observations. Doesn't look a lot alike, because in this particular model, if we only have radial viscosity variations, we actually do not have any of the toroidal flow. So if we look at the poloidal component itself, and you can again do that in the exercise this afternoon yourself, even then, the poloidal component does not look a lot like the observations. Broadly, yes, right, we get the sources and the sinks, but we do not have the strain rate localization that is observed. We do not have plate boundaries in here. And here's the toroidal component. That's the spinning component for the present day. We do not match that. So that means a layered viscosity model is never, ever able to explain plate velocities. And we can do several things about it, coming back to the beginning of the lecture. And one thing we can do is we can prescribe the plate boundaries. If we prescribe the plate boundaries, then we can set up a torque balance by integrating the tractions that are acting underneath a plate. And that gives you the way that this plate is being pushed overall. The integration here is important because if you have a plume sitting under the center of a plate, plate's not going to move at all. You have to push from the side so that this integral has a net non-zero result. You can do an experiment where you take a plate, you push it, and you compute the induced tractions on the other plates, and that gives you a plate-plate interaction. And you can assemble a plate-plate interaction matrix, which is shown here, and that allows you, for given driving forces, to solve for the plate velocities that result from those driving forces. Alex Forte's computation that I showed at the very beginning is based on this approach, and it was pioneered by Ricard and Vigny in '89. And here's their computation: observed plate motions that are predicted by the model, and it works pretty well for their approach, not as nicely as for Alex Forte's model. And you can ask, well, what's missing from this mantle traction sort of approach? One of the things we did, and I don't have that much time to go through this, is to add edge forces and say, if I have a model driven by P wave or S wave models here, how much does the correlation improve if I push a little bit more at the ridge, if I pull a little bit more, and you get some sort of modification. And that becomes more important if you, instead of asking about the direction that the plates are moving, if you're asking about the plate velocities. This imbalance between fast oceanic plates and slow continental plates can be explained, as Clint Conrad and Carolina Lithgow-Bertoloni have pointed out, by having stronger slab pull as opposed to a distributed slab suction force that you would expect for a weak slab. So there's some feeling here in the plate velocities for the strength of the slab. However, there's a non-uniqueness here in that if you take a laboratory-derived rheology, just such as the one that Magali was using earlier, and you then compute the plate velocities without pulling at the slabs, you can also arrive at a model that has relatively fast oceanic plates and relatively slow continents by the existence of a sub-oceanic plate asthenosphere. These colors here indicate the velocities of the motions at 250 kilometers, and then the background of the vectors and the background colors of viscosity. So there's an issue here in terms of strong continents, weak asthenosphere, strong slabs, weak slabs, that is still not that well resolved. And there are attempts here to resolve this by Van Zummeren et al., where they combined different viscosity models with different degrees of slab pull fraction. And what you get out of those is that there's some indication that slabs have to pull more than would be inferred for an isoviscous sort of setup, which is not a surprise. But I think this is broadly consistent with having slabs that are maybe a couple of hundreds, factor 100 stronger than the background mantle. Okay. I want to close by briefly commenting. Michael told me to be done by 12:15. By briefly commenting on seismic anisotropy as another thing that can be explored by these mantle flow models. If you set up a global circulation model with a diffusion dislocation creep rheology, then you have some sensitivity to the grain size. And for the assumption of a constant grain size, for particular assumptions also on the dryness of the material, you get this sort of average viscosity here. And you get a dominance of this location creep regime in the depth region, as Jean-Paul Montagnier explained, where we think that lattice-preferred origin of seismic anisotropy due to olivine is happening. So this is nicely consistent. And we can then take these flow models and use mineral physics models, such as the ones that Rudy Wenck has been developing, or others. Here we're using the D-Rex approach by Kaminsky and others, to take mantle flow and then track virtual rocks and predict the full elastic tensor based on mineral physics models, and then do something with it. For example, compute synthetic seismograms, or look at the overall character of heterogeneity. What these pathological models would indicate is that about 80% are hexagonal character, 12% are orthorhombic, and typically we have about 75% of single crystal saturation, just something that came up earlier this week. So we can generate synthetic models of the mantle. We can query them And we can compare them with surface waves. This is what's done here for the panels B, C, and D. And A is comparing azimuthal anisotropy with paleo spreading at shallow levels. I don't want to talk about this for now, but let's look at those three. The blue sticks, that's one particular model of azimuthal anisotropy based on surface waves. Cyan sticks is an absolute plate motion model in one reference frame. Background coloring is misfit. Here's the match where the assumption for the absolute plate motion model is we get shearing alignment as seen at the surface. You can see that these particular models do slightly, this one does slightly better, reduces some of the asymmetry here. And here's now a flow model prediction where blue means good, red means bad. And you can see that we're doing poorly underneath the ridges, for example, and we think that might be because these mineral physics methods are not doing as good a job in terms of the reorganization of LPO structures as they could. What is fun about these sort of approaches, this is not a done deal, but the seismological models have improved such that when I use Eric Debye's model, Eric's going to be here next week, the answer here in terms of LPO is very much similar, although there's more small-scale structure. So the geodynamic approach, the one that was able to match the geodynamic topography and the plate velocities, does seem to not be completely out of whack, even if we throw this other thing at it that wasn't used to constrain it. We can do this at the global scales. And we can ask tests, we can ask questions. Here's an old test I did showing you the alignment of model and some sort of surface wave anisotropy for a model that has a normal viscosity, this dark line here, and one that has this low viscosity notch at 660 that was proposed based on transformational superplasticity. And you can see that this decorrelation, this decoupling, leads to a complete mess up of the signal in the Pacific. So it's probably not the right viscosity if everything else is sort of okay. And it would be very worthwhile to redo this in the light of recent active source and EM evidence for a decoupling layer at the base of the plate, which I think we could potentially also rule out. So these models are not interesting for all the stuff that works, but they're interesting as tools to see if different mechanisms help or hurt the model fit. Finishing up, we have these global models. That doesn't mean at the present day resolution that we cannot probe them regionally while maintaining this consistency with global approaches. Here's an example for some work that I was involved in, looking at northwestern South America, looking at shear wave splitting observations, the sort of type that Jean-Paul Montagnier introduced in the more long, we'll talk more about. And so you can do the synthetics, compute the global flow model, get synthetic waveforms, do the splitting measurement on the waveforms, do all that, and see how well you can fit the data, the measurements. Here, blue means good, red means bad. That's a particular sort of reference model, sort of a lame background model. We can play with the model parameters, and we can make this match almost perfectly, right? Not very interesting, right? If someone said, if a geodynamicist shows you one model or two models walk the other way, sometimes that's not good advice. In this case it is, because who cares if this is the best model? What did we learn? And we tried to do a little bit better than that. And here's just an illustration of what an inverse geodynamic approach can do. This is showing you different viscosity models, different density models of the Earth. And then in terms of misfit, good and bad, there's these families of models, in particular families of models that have a weak asthenosphere and a strong continental keel that match the data better than others. And this gives us some confidence about the robustness in these observations. And I think, yes?
A lot of people think in the cratons for the shear wave splitting, it's a fossil anisotropy, and that's been the general interpretation. So this would be irrelevant.
Yeah. So this begs the question why it works so well. Here the craton.
Primarily come from the asthenosphere.
So okay.
There is a small contribution from the lithosphere, but most of it is from the asthenosphere, even in continents.
So for the region, the craton sits kind of here. And I think this decrease in delay times you're seeing here is because we're now overprinting asthenospheric flow and frozen in anisotropy. The general problem with invoking fossilized anisotropy for shear wave splitting is that in many regions, the integrated strength you would get from a lithospheric only source is not large enough to explain the delay times. So if you have a frozen-in fabric and some geological indicator that some shear that's frozen in, say from past orogeny, aligns with splitting, that would then say that for some reason a part of the mantle has to be sheared in the same kind of way at the present day. And that might happen in places. But it's really an argument about the anisotropy strength. And I think this separation of frozen in and presently generated anisotropy, is an interesting one, and it can be addressed in a number of different ways. I focused on the flow-based anisotropy, but for example, in work we did on radial anisotropy, we were able to show that we can match part of the signal, and the part that's missing in the old continents is consistent with the frozen-in signature, right? You can sort of bootstrap your way of saying, let me correct for the mantle part and see what's left over and do it this way. Or you can do a joint inversion, you can do a number of things. But I think the general answer is, if you think you have a lithospheric source, check if the integrated delay times are large enough, and often they're not. There were smarty pants here. They are actually quite large, and this partially motivated the study. So here, color. Color is delay time, typically 1.5 seconds. And here we get some really large ones, and we were curious about that. That's motivated it. But the overall number for delay times is about 1.5. And there was some concern earlier that if you take the surface wave models, and Jean-Paul Montanet has been pioneering these sort of things, and Barbara has done a lot of work on that. If you integrate the strength of the surface wave-based models, they fail to explain the strength of anisotropy you'd expect from shear wave splitting, right? And so it appears that the damping, the regularization that is involved in constructing these azimuthal anisotropy models is such that that is a big part of the answer. And if you look at Eric Debye's models, and probably also Jean-Paul's more younger models, those average amplitudes come up closer. Right? But it is still a bit of an issue that it's hard to take a surface wave model that should see the same Earth and get 2.5 seconds, broadly speaking.
I think the discrepancy comes mainly from the fact that the surface waves are not that sensitive below 200 kilometers depth, and in continents, at least under continental keels, that's where the main signal from the SKS splitting comes. It's below 200 kilometers. So if you only have the surface wave signal, you can't resolve it.
My statements are based on the assumptions that a lot of the newer models are using overtones and hopefully have a little bit of a better depth sensitivity. But indeed, if you have fundamental modes only, then you're biased toward the upper 200 seconds. And then the question, we talked about upper mantle, and of course the SKS wave can have accumulated the delay time anywhere along its path coming in from the core mantle boundary. And there are, of course, indications of anisotropy at the core mantle boundary, close in the D double prime layer. And I think Maureen Long is going to talk about this more. However, there are certain places, right, where we have local S and compared with SKS, and there a predominance of the signal from below the lithosphere, somewhere around 200, 250 kilometers, as expected from dislocation diffusion creep modeling is confirmed, right? So we do have some evidence that at least in certain places, SKS samples mainly this sort of upper mantle region.
The flow models you're using here are isotropic.
Not all. We've done tests on mechanically anisotropic flow models. And for the circulation models, it's very hard to disentangle the preferred squishiness from an isotropically reduced viscosity, because most of our signals are sampling the shearing of the plates, and the up and down parts are pretty messed up. In a time-evolving scenario, it appears that including mechanical anisotropy makes things more plate-like. And that, I think, this mechanically anisotropic business is sort of seeing a renaissance right now. Einat Leff and Brad Hager did some of the pioneering work earlier, Louis Moresi, and and folks. And so now with better constraints from the field on the mechanical anisotropy that goes along with the LPO, I think we're going to see more of that. And Clint Conrad is working on this right now with Lars Hansen. But for this stuff here, if anisotropic viscosity does not predict anything larger than about a factor of 50 difference or something like that, everything I said here will be still valid, except the places such as subduction zones and ridges that you might have noticed I've avoided for the most part. So I had a couple more slides, but I can wrap it up. I hope you got a flavor for the degree of knowledge we have, some of the uncertainties. I think we've really come along in a long way, even the last 10 years, and it was fun to update these slides. I think we're going to learn more from inverse approaches in geodynamics, where we're not just quantifying the range of likely best fit parameters, but also the importance on different parameters, and more importantly, where we have guidance as to how to best design experiments, both field deployments and laboratory measurements, to get at the key measurements. I think that'll be awesome. And I think looking at the uplift rates, and in general the verticals, which sends a wide range of scales from post-seismic to post-glacial to convective, I think we're going to learn a lot from that. And maybe I want to leave you with like a little plug for work that Andy Fried and the folks in Japan and myself have done, where thanks to the great instrumentation in Japan, and thanks to the size of this devastating M9 Tohoku earthquake, we're now able to query the Earth on a spatial scale that is the same as the convective timescale, meaning the upper 600 kilometers of the mantle. And we can ask these questions that Uli addressed partially. What is the short-term, what is the long-term rheological response of the Earth? And what we're finding, based on the verticals for the most part, is that there's a good indication of a weak part that sits in the lower part of the subducting plate. Now, this weak thing can be broad and have a relative moderate viscosity drop, as would be expected based on Pyle's creep, as Bruce Buffett and I pointed out, in the exact right depth range. Or it could be thinner and super squishy, as might be expected based on Tim Stern's and others' active source results. We can limit that it goes down, it doesn't go down, and the fun part about this study is that if it's the squishy Tim Stern decoupling, this signal should be gone in 5 years. We should see the decay. So that's amusing, and so in 5 years we can go back and we can at least resolve some of the ambiguity here, hopefully.
How deep does it go?
It has to be weakening this cold thing. We're feeling the cold plate, and it has to be reducing the cold plate. So down here, it's already weaker. We cannot really say that. But
I meant down dip.
There's a number in the paper. It's sort of like it's drawn here. It cannot go down. I think 150 is the limit. 150. Yep. Okay. And I hope. Thank you.
About the weak lower slab layer. So
Yeah.
how thick is it in your models?
Yeah, so it's either thick and moderately squishy, or thin and super squishy. So thin, something with kilometers, and thick would be just like what Bruce and I predicted for the Pyle's creep regime. So I think we're talking about 40 kilometers compared to 5-10 kilometers. But the viscosity, as I said, is the interesting part. It would have to be super weak, and we should see this decay over our lifetimes.
I thought that in that Tim Stern paper that weak, super squishy layer was actually sort of a permanent, that they ascribed it to be a sort of a permanent incoming feature of the LAB or something. So what's the reason for the decay in this case?
Oh, so we cannot say if it exists underneath the incoming plate. We don't have any sensitivity there because where the instruments are, where the earthquake is sensing. And all we're saying is that, let's look at the viscosity structure, and this earthquake might have activated it. So we're seeing decay that is facilitated by a certain viscosity structure, right? And so it may well be permanent, of course, with the caveat that we are still looking at different timescales, right? Now, I think it's a very interesting suggestion that there's this layer, and as I tried to indicate earlier, I don't think our mechanical models of the upper mantle are consistent with a strong decoupling layer because the fit to seismic anisotropy would be much, much poorer. I haven't done the test. I've done the test for a deeper decoupling layer. I'll note that the models we construct do have a weak asthenosphere. It's just not this localized layer. Right? But it remains to be seen. It's an obvious test to make, I think. I thought it was done.
I'm sorry, I was a little bit confused. When you're comparing observations of seismic anisotropy with model prediction, what exactly are you comparing from the model?
Apples and apples. So we're
so
trying to
is
be...
it computed LPO or?
Yes. So we're trying to be as close as possible to the seismological data. And the philosophy is that we don't want to be comparing models and models. We would want to ideally be comparing real data with synthetic data to infer directly what sort of hypothesis test is possible and which one is not. I'm trying to bring up the slide. And so what we did for everything I just showed is we have a flow model. Sometimes it's time dependent. In most of the cases here it's not. We track flow with a mixture of olivine and enstatite using the D-Rex approach by Kaminsky and Riebe.
Okay, so
that gives us the tensor. For the surface waves, we do the averaging, as Jean-Paul told us how to do in '86. For the shear wave splitting, I do a reflectivity method, full anisotropy synthetic waveform computation, and I do a splitting measurement of my synthetics.
Okay. And what about water?
What about water?
Yeah, I mean, would it change things much? Yeah, I should probably not ask that. It might backfire.
Yes. Well, if Corrado's group is right, then there's a strong deviatoric stress and volatile content dependency on the type of LPO that is forming. In all of the computations here, I've used the standard A-type LPO. We've done experiments where we've assumed C-type fabrics, for example, and we've then turned things around and asked, can I improve a dry LPO fit to radial anisotropy on the globe by adding in a little bit of water in a very approximate way? That allows you then to invert for the regions where volatiles might be present. The answer you get is interestingly not too dissimilar from the answer that Trumpere has gotten based on an entirely different approach. I'm not saying we can map water this way, but it's a way to do it, right? Of course, there's an inconsistency then in that the rheology does not account for it. But that's one of the examples where technically it's trivial to do the computation, right? And for instance, Manuela Facenda has taken our way of wrapping D-Rex and has looked into this and has changed from A to C fabrics. So we can do that. There's no problem. The real issue is we don't really know where the water is. And so it becomes more of a problem of what do you put in. But this is all dry, just for the sake of argument, right? But we've done C-type computations as well, and you get a little bit of sieve. So that's a way to improve the model fit, if you like.
Thank you.
I think I saw very briefly at the end you had a time scale versus tectonic or
yes.
topography.
Yes.
Yeah, so I'm wondering in terms of magnitude, whether you think you can decouple climate, tectonics, and geodynamics in terms of their signals, and maybe a location where you might be able to test that.
Yeah. Shallowly, not. Deep, yes. There are scaling arguments for that, but I can, for instance, tell you that Boris Kaus, my former student Claire Steedman, and I, we did simple 2D subduction models with and without erosion, right? And so what happens is that The deep slab doesn't care, but the surface does care, and scenarios such as exhumation will be strongly dependent on erosion or not. So you get very different shallow crustal, short wavelength structure, pretty much the same long wavelength structure. So I don't think, and that's coming back to a discussion we had earlier, I don't think the surface boundary condition matters for any of these sort of convective scenarios. It's super duper important if we want to read topography, if we want to understand crustal deformation. Right. So by the way, this scale, this thing here, is my plug for, wouldn't it be nice if we would get not just topography, but the time derivative thereof. It's an interesting problem because it spans all these different time scales, right? From hydrological to seismic, lithospheric dynamics, and here are the length scales. And I was talking about the part up here with a little excursion here, right? But if we look at GPS signal, for instance, right now, right, and Bridget Smith-Conter just had a really awesome paper linking verticals in California to the seismic cycle, right? And that's great. But if we want to see if there's a little bit of a signal of the mantle actually changing its push or pull, then we have to sort of try to disentangle this. And there's a real issue in terms of the codes, right? Our computer codes that I mentioned earlier can handle all of this stuff, right? But we still have a problem bridging the timescales here, right? And people are working on that, but you cannot just take off the shelf a code that will do wave propagation and mantle convection. Maybe not something you want to do, but maybe you want to do lithospheric deformation in seismic cycle timescale because that's interesting, and Tohoku has some lessons for that. So there's a challenge here in getting the codes to cross these scales.
I have a question about your super squishy or squishy layer.
Yes.
Not only you have the depth, the thickness, but you also have a lateral extent. So with your lateral extent, I would like to know, is there any reason that is cut off and
no
mechanism for it?
This side, right?
Yeah.
This side, no, it's not constrained at all. We should have cut off the figure here, right? We have no sensitivity, so it may well be there. Here, yes. Interestingly, yes. I didn't believe it, but Andy, he said he'd sell his house.
Right.
And that comes because the stations are sitting here, right? And so it doesn't work if we drag it down deeper. That is constrained, I'm told. I will not buy my house. So. Yes, and so that's what Bruce and I argued, right? Bruce and I argued that if you have a material that has temperature-dependent viscosity and low temperature plasticity called Pyle's creep, Bruce computed the bending, and we can predict where it's weakening. It turns out for a Pacific plate, it's just the right age, and we predict exactly the right depth range. So we could go home and be happy, but to be honest, we are noting there's a trade-off, and it could be thinner and squishier.
Okay, that's fine, but I'm just wondering that if, say, your left side is constrained, all right, that's fine with that bending, but then what happens is you follow any mechanism that create this squishy layer.
Yeah.
So at what thermal or chemical conditions you would terminate, or you would have an implication that all of these subduction slabs at some point will develop a weak layer.
Yeah, so, I see. So this sort of lateral extent is presumably broadly consistent with a bending Pyle's creep interpretation. So all the slabs should do that, roughly, right? And consistent with what Magali found in terms of weakening of slabs and other stuff, of course. So, but if evidence shows that this persists as a broad layer, then we can rule out the Pyle's creep, correct. So there's another way of falsifying this. It's almost like we're scientists.
In bending there, just a maximum yield strength, you get a weakening of that lower bending region, exactly like what you see there.
And not when I do it. When I do it, I get the weakening here, and here, and
I
here.
tried to find a figure on my computer. I'll try to find one, and they actually get a very nice, almost like a bending hourglass.
Yeah, but there's no hourglass here, right? There's no reduction up here. That's the thing. It's just the bottom.
Just the bottom.
Swear it.
So then it's over here. Okay, yeah.
No, that's why I don't think it's this instantaneous. It's not this sort of
It's not
plasticity.
just the instantaneous yield.
Yeah, but to be clear, particularly given that I'm on camera, it appears unlikely. But of course, wouldn't it be nice if we could obviously give you some error bars on this, right? And we've done these. So we have plots in this paper that tells you depth of cutoff against misfit, and you can see there's a minimum and things like that. But that's probably more subtle. But I don't think we can have, because we asked, what's happening here in this cold nose, and it didn't like it weak there. Yeah, I know, but the nose here is pretty close to the slab. Yeah, but I think in this model, if it were squishy here, I don't think the data don't seem to like it.
Thorsten, the word squishy is making me hungry. We have an assignment for lunch and this afternoon to think about the questions for our time slot at 4:30. Let's thank Thorsten again.